of length. This visualization shows the process of geological sequestration. The CO₂ plume line structure.
Welcome to Module 7 of our CCUS Masterclass series. In this video, we will explore geological CO₂ storage and the physics of sequestration, covering geomechanics, structural seals, thermodynamics, and regulatory compliance. This video follows a structured roadmap, beginning with site screening, moving through the underlying physics of trapping states, examining the hydraulics of injection, and concluding with monitoring protocols and permitting requirements. Our first section focuses on basin-scale screening and reservoir geomechanics, where we establish the necessary boundaries and geological criteria for effective storage. This matrix illustrates the diverse formation archetypes available for storage, comparing their theoretical capacity, permeability, primary trapping mechanisms, and commercial technology readiness levels. Effective porosity and Darcy permeability are fundamental to site suitability. Ideal reservoirs require over 15% interconnected pore space and consistent permeability, exceeding 100 millidarcies to manage pressure safely. Storing CO₂ in a supercritical state is essential for maximizing storage density. This requires specific depth conditions, including a minimum depth of 800 meters, to maintain the required pressure and temperature gradients. As this graph shows, operating below 800 meters keeps CO₂ in a high-density, supercritical state. This prevents it from reverting to a gaseous phase, which would otherwise threaten caprock integrity due to buoyancy. In Section 2, we investigate the 4 primary physicochemical trapping mechanisms that ensure long-term CO₂ stabilization within geological formations. This security curve demonstrates how physical containment risks diminish over time as CO₂ transitions from mobile plumes to trapped, dissolved, and finally, mineralized forms. Structural trapping is the immediate primary barrier to CO₂ migration. Anticlinal dome enclosures, capped by low permeability rock, function much like natural gas reservoirs to contain injected volumes. Residual gas trapping occurs through capillary snap-off, where microscopic CO₂ droplets become permanently isolated in pore spaces as water displaces the primary injection plume. Over longer periods, CO₂ dissolves into brine, creating a carbonated mixture that is slightly denser than surrounding fluid. This triggers gravitational sinking, creating convection cells that further isolate the CO₂. Mineral trapping is the final stage of permanent storage. In basaltic formations, reactive minerals can rapidly convert dissolved CO₂ into solid carbonate rocks, as proven by benchmarks like Iceland's Carbfix project. In Section 3, we look at the geomechanics of containment, focusing on the integrity of caprocks and the prevention of wellbore degradation. Caprock integrity relies on low permeability shales and ductile salt seals, which can self-heal under stress. High capillary entry pressure and long-term chemical stability are critical factors for securing these boundaries. In this section, we analyze fracture pressure gradients. It is critical that injection wellbore pressure remains safely below the rock's minimum horizontal stress boundary to avoid tensile hydrofracturing and potential leakage. Fault reactivation is a key geomechanical risk. Injecting large fluid volumes can increase pore pressure, reducing effective normal stress, and potentially triggering slip on pre-existing faults. Wellbore integrity is vital for long-term storage safety. We monitor mechanisms like cement debonding, casing corrosion, and geomechanical shear to deploy appropriate engineering mitigations. Portland cement can be vulnerable to carbonation when exposed to acidic wet CO₂. Modern wells often utilize specialized epoxy resin or calcium aluminate cement blends to prevent leaching and ensure durability. Moving to Section 4, we examine reservoir wellbore hydraulics and fluid injection physics, focusing on multi-phase flow, pressure gradients, and thermal cooling effects. Modeling multi-phase fluid dynamics is essential. Here, we track how CO₂ and brine compete for pore paths, using Darcy flux calculations to account for absolute and relative permeability and fluid viscosity. Understanding relative permeability curves is key. As CO₂ saturation rises, brine flow is restricted, which can cause localized pressure spikes near the injection well that must be managed. High-pressure CO₂ injection involves thermal risks. Adiabatic expansion can lead to Joule-Thomson cooling, which may cause hydrate formation, pore plugging, or even thermal stress-induced fractures in the rock. Regulators require managing the area of review. We must account for both the CO₂ plume and the broader pressure footprint, sometimes using brine extraction to maintain stable reservoir pressures. Our final section covers monitoring, verification, and accounting, or MVA. These networks are crucial for tracking the CO₂ plume and verifying containment over the project lifecycle. 4D time-lapse seismic profiling is a standard MVA tool. By comparing seismic surveys over time, we can visualize plume boundaries and confirm containment within the designated storage zone. Advanced sensing technologies include distributed acoustic and temperature sensing. Fiber optic cables provide real-time, high-resolution data on acoustic signals and temperature anomalies, helping detect potential leaks instantly. Electromagnetic mapping provides further verification. Since supercritical CO₂ is highly resistive, CSEM arrays can map saturation fronts and help identify any brine leakage into overlying aquifers. Groundwater protection monitors are essential components of a robust MVA strategy, ensuring that injection activities do not impact local water quality or shallow aquifers. Finally, INSAR satellite technology measures millimeter-scale surface heave caused by subsurface matrix expansion, providing a non-invasive way to monitor pressure changes deep within the reservoir. This video examines atmospheric and surface-level monitoring techniques. These include eddy covariance towers for detecting airside flux, noble gas tracers for chemical fingerprinting, seabed acoustic sensors for offshore leaks, and mobile laser probes for scanning pipeline integrity. Beyond environmental monitoring, operators must navigate regulatory frameworks. This involves Class 6 permitting, managing geological risk, mitigating induced seismicity, and developing long-term liability handoff strategies to ensure project compliance. The EPA Class 6 permitting sequence follows a rigorous path, characterizing the site through geomechanical profiles, modeling the area of review, constructing resilient injection wells, and finally managing long-term injection and site closure. Long-term liability stewardship includes post-injection site care, where operators verify pressure and plume stability. Only after proving that CO₂ is permanently contained can liability be transferred to the state. Geologic capacity is calculated in stages, from total theoretical volume to effective capacity limited by rock mechanics, then practical capacity based on economics, and finally matched capacity within local infrastructure grids. This concludes our module on geological CO₂ storage. For further discussion, research collaborations, or technical training, please reach out via the provided email addresses or connect through the specified professional network.